Hello, everybody. Thank you for taking an interest in this subject. I'm going to spend the next half an hour or so discussing a little bit about Maxon's work in creating motors and gearboxes and drive systems for rovers in use on Mars. So I want to divide this up into about 3 different sections. I think we'll start off with a little bit of general background to the history of the exploration of Mars, because I think that gives a good piece of context. Then we'll look at what kind of motors and what kind of applications Maxon has actually been producing for use on Mars. And then we'll look a little bit on how the development process works, so that when we deliver a motor, we can be confident that it really will work. So first, a piece of background as to why are we going to Mars at all, because I think it's important to keep that in mind. Of course, there's a scientific background to this and an exploration background, and primarily it's because people view Mars as the only really likely body that's close to us in the solar system that we have a chance of going to live on, or that has in the past had life on it, or may have life, or may even still have life on it. And the reason for this, of course, is the temperature range on its surface is not completely dissimilar to on the Earth. It's somewhat colder, but not impossibly so. The amount of surface area is very similar to the Earth's, even though Mars is significantly smaller because, of course, it has no oceans taking up any space. So surface area on Mars is similar to surface area on the Earth. The atmosphere has the oxygen in it, although it's not free oxygen, but that means it could be extracted. Even if there is no life there, it's geologically interesting because it has volcanoes, it's had movement of its surface. That's why it has these canyon systems. We've now shown conclusively that there's water on Mars, which of course is another firstly geographically interesting feature, but if we're going to go there as humans, then we don't have to drag water with us from the Earth. And of course it's relatively close, although the word relatively is important there, and that means that the size of the rockets that we need to send spacecraft there is not too large. So it's been known for thousands of years that planets are different to stars because they move relative to the backgrounds. That's where the Greek root of the word originally comes from, meaning a wandering star. But for the first several thousand years of knowing that they were different to normal stars, there wasn't really much more that we could explore about them because as our naked eyes see them, they're only a spot of light in the sky. And it was only really with the development of telescopes in the 1600s that it became possible to start really exploring what the planets are, and in the case of Mars, what is Mars like. So as you can see here, with originally the earliest telescopes enable you to resolve the disk of you can see it's now a world, but you can't really get any further than that. And even as you get to fairly large telescopes, as these ones that were developed sort of 150, 200 years ago, the amount of detail is very limited. And unfortunately, astronomers 2 centuries ago or so managed to sidetrack themselves by making up the details. Effectively, I think is the way you could phrase it. And there's these very famous canals on Mars that studied by several people, in particular Percival Lovell. And you can see the maps that were drawn here, and there was all sorts of theories developed about civilizations on Mars, and it was dry on one half and wet on the other half, and they were needing to move water around. And of course, it was all completely made up. Not deliberately, but they were certainly convinced they could see these lines, but they were just artifacts either of reflections from the veins in their eyes, or maybe in defects in the glass. The 2 leading theories there. Even when we moved to the middle of the 20th century, when these sort of very large telescopes were built, this Mount Palomar, which was a battleship quantity of steel used to construct it in the mid-1940s, it still can't really see very much about what's going on Mars. And even today, if we show the Hubble Space Telescope picture here, that's pretty much the best we can do. Even now, you're still fairly limited. So you have to go to Mars with a spacecraft in order to be able to determine more about its geographic history. So the picture we see here is from Mariner 4, which was the very first successful flyby of Mars, and it was unable to go into orbit because that's a significantly more complicated process. So it flies by, takes a series of pictures as it's going past, and then develops them on board and then sends the pictures back. Unfortunately, the area that it went through whilst it was taking these pictures turned out to be one of the least interesting parts of Mars as we now know about it, and it was a heavily cratered area, and I think scientists were very disappointed at the time, really expecting something a bit more interesting than just more moon-like pictures. But people kept going, and then orbiters were developed, and by the early 1970s, it would successfully put Mariner 9 into orbit around Mars, and then that was able to map the entire surface. And the mapping of the entire surface showed what we know about Mars today, and that it really is geographically much more interesting. It has these volcanoes you can see there, giant canyon systems, significantly larger than the Grand Canyon, for example, and features that look very much like they may have been carved by flowing water, or at least flowing liquid of some kind. Once you've gone into orbit, then of course the next step is not just to be in orbit, but to go down and land. And that was achieved in 1976 by the Viking landers, and you can see the approximate size there. That's actually Carl Sagan standing next to the lander, and you may have heard of him from the Cosmos series, TV series in the early 1980s. He was a very well-known astronomer who pushed the development of solar system exploration and was very much into the public outreach aspects of that. You'll also notice here that there's an arm visible that could dig trenches, and that, of course, is the first time that a motor was on Mars, at least used successfully. This was well before Maxon was involved in the space business, but that was the first successful use of a motor on Mars. Once you've figured out how to land on Mars, the next thing you want to do is move around, and that, of course, is where rovers come in. And what are the advantages of rovers? Why have we now, over the last 20 years, seen a number of rovers flown? So firstly, the obvious advantage is you can develop your exploration over a much larger area. It's not just the one point where you land. Since landing is the key to everything, it's no use going to a very interesting but unstable geographical area. So it's just like landing in the Alps versus landing in the Sahara Desert. The Alps are much more interesting to look at, but if you land on the side of a mountain and you tip over, then that doesn't do anything for you because you've lost your entire mission. So you always land somewhere safe. And that led to the landers not necessarily being in the most interesting locations scientifically. The solution to this is the rover. You land somewhere safe and then you drive to the interesting areas. There's other ways of moving around, of course. You could try flying or something like that, and this is something that's going to come in the future, but it's not as technically difficult to have wheels and drive around. So what do we need to be able to build rovers? And there's a number of key features that I'll show here. The main purpose, of course, which we mustn't forget, is to get our science instruments, whether these are chemical analysis or just the camera systems. That's the main reason we're going there, is to get those to their targets so they can collect data and get that data back to the Earth. So getting the data back to the Earth means you need the radio communication system, but that's a fairly well-known technology, and as far as space systems are concerned, they've been around since the 1950s. Then you have to power your spacecraft. Mostly what is done these days is with solar power, especially on Mars, but that's not the only way of doing it. On both the Viking landers and the Curiosity rover that's driving around at the moment use plutonium pellets to generate heat, and then the heat is passed through a thermocouple, which is cold on the outside, hot on the inside, and generates power that way. But those are big and heavy, expensive, and have political issues attached to them. So the push is definitely to more solar powered systems. But again, these are technologies we've known for quite a while. The camera systems, again, they've also been around since the 1960s. They may be much better now. We may be able to fly many more of them. You can have navigation cameras and your science cameras and engineering cameras, all with different functions. But again, there's incremental improvements there. But when we came to the late 1990s, when the first rovers were being considered, it was really motors that were the key thing that hadn't been flown in that kind of style before. So the only previous experience of motors in vehicles for out off the Earth were the lunar landers, the manned ones that were flown in the Apollo missions, and the unmanned Soviet ones, which you can see on the bottom left here. But those were completely different styles of motor. One of the big issues you have to deal with is how do you make your motor work in a vacuum, and in both these cases they capsuled them inside pressurized systems so that I didn't have to deal with that issue. And that's not really the way that it's practical to do on a much smaller spacecraft. These were, of course, fairly large vehicles. So motors, that's our segue into Maxon. And I don't really want to say too much about Maxon other than what is needed to understand what kind of company we are and what it is that we produce. This isn't intended to be a sort of a review of Maxon as such, but basically Maxon produces motors, gearboxes, and feedback devices. We also do electronics, but none of our electronics are for space applications. And these are a whole mass of different sizes, and they're ranging from 4 millimeters up to 60 millimeters in diameter. And the motors are divided into two basic categories, which is brushed and brushless. And for all the historical Mars missions that we're going to be looking at here, we're talking about brushed motors. Maxon itself is a Swiss-based company in the canton of Obwalden, so they're not too far from Lucerne. The geographical center of Switzerland is just a few kilometers away from the factory. We produce about 4.5 million motors a year. That sounds like a large amount, but there's other motor manufacturers who make that many motors every week. So we're actually a niche player. If you want to make huge numbers of motors, we're not the right place to come to. If you want car wing mirrors or something like that, motors for that, where you want millions of them, that's not Maxon's business. But if you want some specialist application and you want to buy somewhere between 100 or a few thousand, and you need lots of modifications, that's sort of the core that we do. And you can see here, if you take the 16,000 different variations that we do per year, 4.5 million divided by 16,000 gives you roughly the lot size. There's about 2,500 people worldwide, and just as of last year, more than half people employed are now outside of Switzerland. We have factories now scattered around the world, and this is a growing trend for us. We were originally just a small family-owned company based only in Switzerland, and although we're still family-owned, are in the process of turning into really a worldwide, internationally active company. And from the locations you can see on here, the relevant ones for the Mars motors, the factories that are involved are Switzerland, Germany, and Hungary. So I could spend a lot of time discussing about details inside motors, but I think what's more interesting really is just to look at the one example here of a summary of a kind of motor that's flown. This is fairly similar to what was done for Spirit and Opportunity and what will be performed for ExoMars coming up, which I'll explain a bit more about what those missions are in a minute. But fundamentally, what you see is a copper. That's the gold winding. That's the gold color in here, which is self-supporting. It rotates, it's fixed to the shaft and rotates around the black magnet that you can see in the middle there. So it's a permanent magnet, and that's fixed on the stator. So there's not very much mass on the rotating part here, which makes it very dynamic. Because there's no iron core, so there's no stator sheets in here. That means that there's no eddy current losses, and that makes the motors very efficient. So you can get well into the 90+% range of electrical to mechanical conversion efficiency. When we're talking about brushed motors, we're talking about the brushes. Those are the sort of coppery gold sections on the far right, which conduct the power coming into the motor onto the shaft so that we can select the correct part of the winding to activate. The winding creates a magnetic field, and that reacts against the permanent magnet and causes the rotor to rotate. And then on the left, in this case, we're going into a gearbox, which takes the high-speed rotation from the winding, from the motor rotor and slows it down to a lower, maybe more usable speed, and at the same time increases the torque that's available. So it's sort of the core of what a motor does. And then the final sort of background before we go back to Mars. Although Maxon is very well known for its space applications, this is not by any means the main part of what we do. 50% of our turnover comes from medical applications, and within the aerospace business units, the majority of our turnover is coming from commercial aircraft applications. And just to give one example of what that means, here the Boeing 787, every aircraft has 44 motors in the environmental control system and a bunch of other motors in other applications. But just looking at the environmental control system, there's 2 of these modules underneath each wing, which provide cabin and electronics cooling, and there's a whole bunch of valves in there and doors on the outside of the aircraft that need opening to let air in, and that's what our motors are used for there. So, what kind of rovers have been flown so far? So the first point is most people who know something about this always say Pathfinder was the first rover on Mars. Well, that's not true. The first rover to land on the surface of Mars was actually Russian in 1971. Soviet Mars 3 mission. This successfully landed during one of the global dust storms that Mars periodically has. And probably due to that dust storm, although the landing was successful, the rest of the mission wasn't. It unfolded its landing system after touchdown. It continued to send data back after touchdown, so we know it was a soft landing, but only for 30 seconds. So, and then it was just in the process of sending its first picture frame back when it failed, and nothing was ever heard from it again. So the rover was never deployed, but it was still the first mechanical rover that was placed on Mars. So the first successful rover, therefore, is Mars Pathfinder, and this was very much a engineering test to see was it possible to develop the technologies that are needed. So it was a fairly small rover. It had these 6 motors for steering and 6 motors for drive. These were lightly modified industrial standards motors from Maxon when they were developed in the late 1990s. And the purpose really was just to show, can you get the rover down? Can you have it drive around? Can you have it communicate? Can you figure out how you're going to be doing your driving and where you want to go? And it had just one science instrument to go and do analyses on nearby rocks. But it worked very well, and that then laid the basis for the development of Spirit and Opportunity, so the Mars exploration rovers, often referred to as MER. And there were 2 motor types in there. Almost the entire rover was used these 2 different Maxon RE20 or RE25, so the numbers refer to the diameter in millimeters, and the RE just means rare earth permanent magnets. So both of them brushed motors. And as I think most people have heard, Opportunity is still driving around some close to 15 years later after landing. It's covered over 40 kilometers. And to bring ourselves back to this point about why are we going at all, it's of course to do the science there. And this picture that's shown at the bottom there very clearly shows evidence of this being a lake bed. All the layers you can see in the rocks there are caused by sediment being laid down at the bottom of an ocean, or at least a lake. And that was one of the key results that's come out from rover exploration over the last 15 years or so. There have been a couple of follow-up missions to remind ourselves again about these results. I think these are 3 of the more interesting things. So the one at the top left there again is showing the arm analyzing rock that's clearly been worn smooth by water flowing over it. The engineering work has been continuing on the right there. You can see that lots of work has gone into development of how these rovers drive and autonomous navigation to move around rocks and things automatically, so you can get more driving distance per day. And maybe one of the more interesting features that wasn't expected at the bottom there are the dust devils on Mars. These have had the big advantage that they periodically go over the top of the rovers and clear the dust that gradually accumulates on the solar panels off again. And that's one of the reasons why Opportunity has lasted so long, because it gets its panels cleaned and continues to get enough power. So there have been a couple of follow-on missions that are not rovers, and these have used leftover hardware from the MER rovers. So this is the Phoenix lander from about 10 years ago. It had an arm on it that also used the RE-25. You can see here the sample collection arm. The MSL, or Curiosity lander rover, which is currently driving around on Mars, used American-sourced motors because this was very much built during the strong period of the U.S. Or George Bush's buy U.S. policy. So it does have some parts of Maxonos, in particular the encoder pole wheels, but we built backup motors here because the company that was selected to build the motors had significant problems. At one point, it wasn't clear whether they were going to make it or not, so we developed these backup motors, but in the end, they weren't needed. So encoders are the only input from us on Curiosity. The big development that has been going on now for the next 2 years, I'll come back to the 2018 insight in a minute, is ExoMars, which will fly in 2020. And here we've been working closely with the European Space Agency and its prime contractors to develop virtually all the motors that are being used on the ExoMars rover. And you can see all the different sizes and variations here. This has been a huge challenge for Maxon's engineering group because of the number of variations that were required here for all the different functions on the rover. Now, the rover itself maybe looks fairly similar to the Spirit and Opportunity rovers, but there is a big change on the type of science that it's capable of performing, and that's the main justification for it. And the drill box that you can see, this black area in the middle of the picture here, is capable of drilling 2 meters down below the surface and then bringing samples up from 2 meters down below the surface. And of course, these samples have then not been affected by either sun or wind erosion on the surface. The drill you can consider to be a little like a drilling platform for oil, where you have one section after another that's placed into the ground. In this case, of course, you don't have an oil rig worker in a yellow suit putting them in the ground covered in oil. Instead, you have to have an automated mechanism, and that's what we see here. That's capable of taking up to 4 of these 50-centimeter long segments, pushing them one after the other into the ground, and then bringing them back up again. And of course, all of that needs a whole mass of different types of motors. Once the samples have been brought back up, then they go into the sample preparation and distribution system. The samples get crushed, turned into a powder. That's what you see at the bottom right here. The powder then gets taken into the carousel that's on the left there. The carousel contains a series of ovens, and each sample gets put into one oven. Then the oven has a lid that can close on it, and it gets heated up. The gas comes out and goes into a spectral analysis system, and the composition of the samples can then be analyzed. There's also the main drive system, which consists of the drive wheels, their steering system, and the deployment system that's needed to unfold the rover after it's landed. So all of these motors come from us. If we just look at maybe the drive system in a little bit more detail here, we have at the bottom left the gearbox on the front, then there's a brake in the middle where also the mounting flange can be seen, then the motor itself, and then on the back an encoder, which gives feedback to the speed at which it's rotating. These motors then get wrapped up in heater foils. That's what you see in the top center, when various cabling and shielding applied to them. The heaters are needed to warm the motors up after each Martian night, so it can cool down to as low as minus 130 degrees C. And we need the motors at minus 55 before we can safely operate them. Then we've been working closely with MDA in Canada to develop the actual actuator that you see on the right there. The motor goes inside that, and this is then what actually drives the wheels forwards. One of the reasons that we are producing these is because of the industrial capabilities that we have for series production. So the majority of space companies who are very specialist companies, of course, for building satellites, generally are used to only producing a handful of each device that they're building. And in this case, 70 systems were needed for the wheels and the drive system, and that's where Maxon's industrial capabilities came into play. And the pictures that you're seeing here are the 9 flight model drive systems. So the best 6 of these 9 will be installed on the rover and will actually fly to Mars. These are all produced in very high cleanliness requirements, so in clean rooms. The main reason for this, of course, is the rover is, besides the fact that it's a space application and you can't have extraneous dust or other materials in there, but the other key reason is the rover is going to be looking for signs of life, and the chemical analysis that we'll be doing will be looking for molecules that come from what we understand life would look like. And of course, therefore, we don't want to be detecting Maxon employees. And so that's why we're all dressed up in the clean room garb. So I said I'd briefly touch on the InSight mission. And this is going to Mars as we speak. It was launched just a few weeks ago before this presentation was recorded. And it will be the first of our modern style DCX motors to go to Mars, so that's slightly different to these older ones that were flown 15 or 20 years ago. Very similar to the industrial standards that are used for all sorts of Earth-based applications, but with certain modifications to make them more robust and vacuum compatible. The InSight mission is not a rover; it's a fixed lander. And it has 3 main instruments on it, and one of them is this heat flow and physical properties package that's developed by DLR in Germany. So it's the German aerospace research organization, and it has what's called a mole inside it to take a temperature probe some 5 meters below the surface of Mars. And it does this with a system that functions very much like a pile driver would do on a building construction site, where you take a mass and you hammer that mass up and down enough times, and every time you bang it up and down, it moves down a little bit. So over the course of maybe 1,000 bangs, this mole will bury itself into the ground. And the motor, which you can see its location here, winds up a spring, and then the spring releases and sends out the shock, which moves it down a fraction of a millimeter, and it just keeps repeating that until it's bored its way all the way down. This will land in November this year, and the mole will be deployed probably in December or in January of 2019. Our trusty RE25 is still in use here for the deployment of the solar panels, which of course also is an essential function here. I won't say too much more about some of the future missions. There's going to be more press releases coming out on these over the next few months, but there are plenty of exciting new missions still being planned. JPL's Mars 2020 mission, so that's NASA's next mission to Mars, which will launch at the same time as ExoMars, is basically a copy of the Curiosity rover, but with a different set of instruments on board, and in particular a sampling system where they will collect these samples, as you can see on the left there. They will go through a sample handling system that will take samples and put them in sealed tubes. These sealed tubes will be dropped on the surface of Mars and collected in a later mission and brought back to Earth. So this is the first stage of Mars sample return. And then just 10 days or so before we recorded this presentation, the Mars helicopter was announced by NASA. This has been in development for the last 1 to 2 years. and is a very exciting example of where we'll be flying helicopters on Mars as a next step of mobility on Mars. So I'd like to move on to the final part here, which is describing how we develop motors for use on Mars. So how do we take an industrial motor and end up with something that's suitable for use in a completely different environment? And this chart sort of shows the main development steps that we go through. So we start off with a industrial standard from our catalog. We have our specifications from our customer. First of all, we just make a few simple changes so that we can quickly check whether we have the correct electrical parameters and the correct properties from this motor, and that's what we call the breadboards, and we do some initial testing on those. If that confirms that we've electrically selected something that has the right power, then we go and develop what we call an engineering model, which is supposed to incorporate most of the changes that we need in order to be able to then perform environmental testing on it. So by environmental testing, we mean things like vibration or shock or temperature range or things like that. After we've done initial testing on it, then we find out what works and what doesn't, and then at that point you correct any problems that you had, and hopefully then have a final design which you build as a qualification model first. This then goes through a formal series of qualification tests where you try and simulate everything that the motor is going to see before it's on, or whilst it's on Mars. And I'll show some examples of that in a minute. And assuming you pass that, then you can build your flight models. So that's sort of the, at least in theory, the sequence that you should be going through. Due to time pressure, this sometimes gets parallelized, which brings its own problems. But these space missions, of course, because they're waiting for launch windows from when the planets line up, the planets, of course, won't wait for us humans if we're not ready. So when they line up, you have to launch. If you don't, in the case of Mars, you have to wait 2 years before they line up again. And that produces a certain amount of pressure for project schedules. Just to give an example here, this is of what we mean by these, how these could look differently for the different models. This is also for a space application. On the left, you see the two catalog-based products that you can just pick out of our catalog. We then put them together in a breadboard that you see in the middle there. So all we've done there is taken the motor type with the winding type that we think we need to give the correct electrical performance. We've taken a gearbox with the correct gear ratio in it, and we've modified the output shaft so that it fits to the customer's interface. After that was successfully tested, then we go and build on the right. You can still see the interface is the same. We build the fully redundant system, which has 2 motors on it, and where work's gone into doing reducing mass internally in the gearbox. And we've applied a whole bunch of the modifications that you need in order to make something space-rated. So you can see that these can look significantly different. So having then built your engineering model, or when you go on to your qualification tests, what kind of things are we testing? So what would a Mars mission need that's different? And it's really to do with the launch with a rocket, so that's where your vibrations come from, and the staging of the rocket. So when stage 1 separates, for example, that gives you big shocks. Mars has this enormous temperature range, going from minus 130 degrees C at night up to an ambient of about 20. But of course, if you're in a housing and the motor's running, that can go even higher. So it's more like plus 100. All the variation of atmospheric pressure from operating here on Earth during testing to being in a vacuum on its way to Mars, to having the CO2 atmosphere, 8 millibars of CO2 on Mars. And then, of course, there's the radiation. Here on Earth, we're shielded by the Van Allen belts, but as soon as you're outside of those, you're exposed to all the radiation coming off the sun and from interstellar space that penetrates the sun's magnetic field. So we test these things. That's the way to be sure that what you're going to fly is going to work. So we have facilities. On the left here, there's a shock table. So that sort of platform that has the motors mounted on it rises up, and then it bangs down with a controlled force. The chamber on the top right contains a shaker inside it and can combine that with temperature cycling. So the picture in the middle is view inside of that chamber, and that's the shaker plates that the motor is mounted to. We have to be able to perform thermal vacuum testing. So we've built this chamber that has a mechanical feed through that if we need to, we can put the brake on the outside. But what we're looking at on the right there is one where the brake, that's the black area, fits inside. The test motor is on the right, it's coupled to the brake, and we program the brake to put the loads that we need onto the test motor. The test motor itself is mounted on a plate, and that plate we can pump liquid nitrogen through and set the temperatures that we need. That valve that you can see at the top left with the black handle on it, that's a leak valve to allow us to leak CO2 into the chamber at a given rate so that we can simulate the Martian atmosphere. So now we know that we can survive travel through the vacuum there, we can survive the temperature cycles, we've shown we can survive shock and vibration. So then we do lifetime testing, and on the table on the right there shows the test units, again with a whole mass of brakes on them. The brakes are programmed by the computer on the left to simulate the cycles that the motor has to go through, and then we'll test these for months to get the required lifetime onto the motors and the gearboxes and show that they're capable of surviving long enough. Radiation we can't do internally for obvious reasons, but there's external laboratories that we can go to, and we take our electronic components that are inside the motors. This is a test facility in Madrid. We lower them down into this water tank, so that water's there to protect the humans, and then we expose them to the required amount of radiation, and hopefully they survive. In this case, they do. We have to make modifications. You can't just fly the industrial standard motors, because we know from experience they won't work. So just taking a few examples over these two slides to show what kind of things we have to change. If we start on the right half here, the left-hand gearbox in this case is an industrial standard one, and there you can see how we have a differing materials. So there's a black coated steel ring gear housing, there's a brass front flange, steel bearing, and steel shaft with press ring. The problem of these different materials is each material has a different expansion coefficients. So you change the temperature, make it hotter, it expands slightly, you cool it down, it contracts slightly, and they do this at different rates. And that means that any press fits, for example, which may work fine at room temperature, can stop working at low temperature or at high temperature. So the first thing we do is to change all the materials so they're as close as possible to being the same. And then things like press fits, we would change to being welded, or if possible, get rid of fits altogether and just make a more complicated part. The bottom left section shows the brush system. Standard brushes have relatively long arms on them because that's a wear part, and the longer you can make the arm, the longer the motor will last, and that's what you want if you're a factory application, for example. But these long arms are also vulnerable to breaking under shock, and that is in fact what they do. We had plenty of failures with shock tests at the beginning of the program, so you have to shorten the brushes. The normal shortening we do is the middle one, and something like Insights, where, as I said, we have the 100,000 shocks, we make them quite a lot shorter. There's also changes you need to improve the inspectability, that's probably the way to term it. So the example you're seeing at the top left there is we have a whole bunch of solder connections to solder the winding taps onto an internal PCB, and you have to be able to inspect these properly. And there's a black carrier for the PCB, and in the industrial standard, which you see here, you can't see the bottom of the solder joint, so you can't inspect it. In order to be able to perform the 100% inspection that you really need for a space application, here we modified the parts, so it's now this sort of star shape on the inside, and now you can come in with a mirror, which is what you're seeing on the right there, and you can see the bottom on the side of the joint and confirm that the solder joint is correct. Just a few more examples. Again, on the right, standard industrial design has the rotor connected to the stator with a bearing, and the bearing is glued onto the rotor and it's glued onto the stator. And under a big shock, both of those glue joints will fail. That's what we've seen in testing. The way around this, it's not really a good practice to weld bearings, so we don't do that. Instead, we weld a plate over the front, which is what you see on the left there, and the plate holds the bearing in place. And then the pinion that's on the front there butts up against the bearing and also holds the bearing in place. And then the pinion we can weld on. The bottom left there shows magnets. So normally we would glue magnets onto the shaft. Firstly, that glue connection is a worry, and secondly, it's possible to have failure scenarios where bits of the magnet break off and then jam the rotor. So in this case, we house it in a stainless steel housing, and we do the same for the steering rotor that's on the back there. That would normally just be glued on. Here it's housed and then welded on. The top left here is also a common problem, that the winding taps going from the winding onto the PCB have several millimeter length, and those can start vibrating or resonating, and they break off. So we pot that whole area. That's what you see on the right hand picture there. So if we do all of this work right, and we test all of our changes, and we've applied all the correct changes to them, so all the correct tests to them that represent what it's going to see when it really does fly, and you then build them with all the documentation that you need to show that you really have built them the way you designed them and the way you built your qualification units, then you don't really need to worry too much about whether they're going to work or not. At least that's the theory. So to close out here, this is the main drill drive unit for ExoMars. So there's just one motor. It's absolutely key. It's a pretty big 40 millimeter diameter motor that will make the drill bore down into the surface of Mars. And to give an idea of how many people work on this project, we discussed with our direct customer and reserved 50% of the surface area of the motor for marking the names of all the people within Maxon who worked on this project, and there's some 120 names on here. So it takes a lot of people to design, qualify, and build the motors that you need for something like this. And what we, of course, now want to be seeing, I started off at the beginning of this presentation with a picture of Mars taken from the Earth. And I'm going to close with, this is from Opportunity, with a picture of the Earth and the Moon taken from Mars. And we hope to see something like this from the ExoMars mission when it flies in 2018 and sorry, in 2020 and lands in early 2021. Thank you for listening.